Already?
Yeah.
Okay. So we're gonna do FRQ2, right? We're gonna do Model E, right? So I'm always switching cameramans, right? People. So thank you, right? So let's do this. We're gonna do FRQ2. So you always want to start off by getting your points, right? So what are my points here? For starters, what are the points, or some of the points here are, I'm gonna have t, and then my y is gonna be s of t. So my inputs are t equals to 0, you have 6, and then you also have 9, right? So for 9, they already gave us our output, which is 25. So now, before I start, 6 and 0 don't have an output. So what needs to happen is that you need to go and borrow this 6 and plug it in to this one, right? The first equation. The reason we do that is because we're simply just trying to obtain an output for 6. So I believe 7 times 6 is 42, then the 0 it's 420, right? So all it is that we're putting in this input in there to get an output, because this equation is easier to obtain than having an A and B there that we need to focus on, right? So in theory, it makes sense. So for 0, you plug in 0 and 0, right? So in a sense, here's how to go about it. So now that we have our points, you follow through with the equation, right? What equation am I going to use for 6 now? So 6, if you look, this is where you want to start, right? So this is what we call the piecewise function. It has different functions that are being tackled at the same time, right? So first, starting the domain restriction. Again, domain restriction because here you have your input that they're focusing on, here and here. So now, to go about this, look at that 6 that we have as an input. From here, it's asking us, is that 6 that's an input between 0 and this 6? Technically, yes, but here you will need to have an equal symbol, right? And this inequality, and which we don't have. So basically, we're going to have to use this one right here. There's the equal sign or symbol. So now plug in your points, because in A1 it's telling you, right? 2 equations. Because again, we have 2 points. This one, in theory, doesn't work out. So now write 2 equations. So the first one, equation 1, input output. This whole thing, S of t, represents your output. So your output is 420 equals A times B, and then with the degree of an input of 6. Get the second equation. Now you have 25 equals A times B to the input of 9. So from here, what we have to do is that, let's verify. Before we move on, let's verify. Let's see if we got a point, right? So did we get a point in A1? In theory, yeah, we did. Check it out. They did multiply 7 times 6, which they gave them 420, and they have the same setup as us, A times B to the power of 6. So this piecewise function allowed us to use the first equation to find our output for 6. And then, in theory, if you think about it, now, because of the inputs being 6 and 9, which are both greater than or equal to 6, we just managed to focus on this one. So this equation may look very familiar. This equation is exponential. So all you have to do is literally go to decimals, insert your table, there it is, and then 6, and then I have 420, and then over here I have 9, and then I have 25, and we're going to apply regression. Regression being exponential, which I'm trying to find it right here. So there it is, right? So now, if we go back to the problem, right? Let's see where our value for A and B are. So yeah, A is equal to this number right here, and B is equal to this number right here. So now let me erase this, because in theory we already got a point for this setup. So I could get rid of this. Let me get rid of all these markings. Get rid of this. And now, if we go back to decimals, you're gonna notice that, hey, it is literally right here. This is A, and this is B. So you get another point, right? So let's go on to part B. So part B is asking for, let me scroll down. Part B is asking to use the given data to find the average rate of change. Part B, just so you can note, it's always going to be linear. So I have to go back to the decimals and switch my regression into linear. So if I go back, where is it? Boom. I'm going to switch exponential and I'll put it as linear. So there it is. My slope, based on this equation, should be negative 131.66667, right? Without the x, no x involved. So now let's double check. Let's double check my answer. So if I go back down here, this is because I need to scroll down too. You're gonna notice, hey, it's right here. Ta-da! So now, 3 points. What is it asking us for B2? So in B2, it's asking to find the average rate of change found in BI to estimate the amount of snow in the driveway for time at 7. So literally what that means is that in order for you to get another point, you go back to decimals. Now, I'm just gonna copy this equation, sorry. I'm gonna copy it. Oh man. It's messing with me. So you're literally, dude, it's messing with me. You're gonna copy it. Please work. Oh, no. It doesn't let me. I'll just write it. I'm just gonna put y equals negative 131.6667 x plus 1010, right? So I literally just copied it, right? But our input, right? They want us to focus on what would be our output if t equals to 7. So what you have to do is literally get rid of this x, because we're gonna input the 7. You press on shift, press 8, you get that multiplication symbol, and put 7. There it is, 288.333, right? So let's double check that was the input that we were looking for. And yeah, it is, it's right here, right? T equals to 7, so let's check our answer. So yeah, 288.333, right? Remember, it's 3 numbers after the decimal. So now, let's go back over here. Let's go back to the question, right? So for B3, it's asking, consider the average rate of change of S. S is focused on this one, the piecewise, right? Which was focused on exponentials. So it says, consider the average rate of change of S from t equals to 9 to t equals p. P representing any number greater than 9. Are these average rate of change less than or greater than the average rate of change of t equals to 6 to t equals 9? Our respondent I. Explain your reasoning. So now, all that means is that it wants us to compare this linear regression, which in theory we call secant line. It wants us to compare that one to our exponential, which is this one. Let me zoom out a bit because we're in the we're in the big numbers, right? So what's happening? So for starters, let me see if this one copied correctly. Maybe. Yeah, it's a very slight change for that line. So what happens? So one of the things you could get partial credit for, somewhat credit for, right? That's to mention the concavity for B3. So for B3, it is concave up. So in theory, average rate of change is increasing. So let's double check it. So it says here, yeah, it does mention concave up, right? So since it's concave up, the average rate of change, right, are increasing. So partial credit, right? So honestly, when you compare these two graphs, in theory, right, I wanted to focus on x being greater than 9, but this is basically a very tight spot, right? Very tight spot. So let me zoom out a bit. So what am I trying to say here? So I'm just going to read out the answer, right? So it says the average rate of change of S from t equals 9 to t equals anything greater than 9 is greater than the average rate of change from this secant line. So because S is exponential with B being less than 1, the graph of S is decreasing and concave up. So therefore the average rate of change in cubic feet per hour are increasing, getting less negative over equivalent input value intervals as t increases. Again, mention the concavity, right? It may sound gibberish, but might get partial credit. Who knows, right? Depends on the grader, but there you go. So I'll leave that there so you guys could analyze it for a bit, right? But it's basically comparing the secant line and the exponential. So now, let's do the last part. Let's see if we can get the last part on our own. So, Mr. Passwater plans to shovel snow until there is no snow left remaining on his driveway, right? I forgot we were talking about snow. I didn't even read the question, but, Mr. Passwater plans to shovel snow until there is no snow left remaining in his driveway. Explain how this information can be used to determine the main limitations of Model S. Model S again being this, right? The piecewise. So what's happening? Let's go back over here. Let's go back to decimals. So what is happening here? So why is this function limited? So if we drag it and just follow through with it, right? It seems like snow tends to basically be at 0 or 0 out after we reach about 13, 12? 12 and onward, right? So let's see what the answer is. Let's see what the answer is. So the answer with reasoning to get a point says Mr. Passwater plans to shovel snow until there is no snow left remaining on his driveway. That is a value of t when he will stop. So basically when the output is 0, right? So s of t is decreasing for the exponential function and would therefore get arbitrary close to 0. So basically what we just analyzed, if you go back to the graph, eventually this will stop, right? And there's not going to be no more snow for this graph to continue. So in actuality, the graph is going to be restricted somewhere along here, which is the number that we said earlier about around 12ish, right? Which you can mention. So in theory, this domain is restricted because after that, there's no longer snow to clear up, right? So there you go. Hopefully this makes sense. Hopefully this helps you guys, and bye-bye.